This conference will now be recorded.
So guys, we have to see what is an algorithm called Kruskals to find a minimum spanning tree. I hope everyone is aware of what exactly is a minimum spanning tree. So a minimum spanning tree is a tree with the minimal cost of weight on the edges and making sure that we touch down all the vertices and there should be no cycles, right? So last time we did see what is Soling's as an algorithm, and today we're gonna see Kruskals as algorithm, and we'll try to implement it. But what I'm gonna do is I'm gonna write a partial implementation. I'm gonna leave a small use case for you people to implement. All right. So let's see how this Kruskals algorithm is going to work. First of all, this is this visualization for the algorithm. I'm just gonna share the link over the chat. If you want, you can open it. So I'm using this graph, example graph CP414. This is the example graph CP414. So Kruskal's algorithm, how it's gonna work for us, right? So the first thing first is we're gonna sort all the edges of your graph. So let me come here, slow it down. So the very first thing is that you're gonna sort all the edges of your graph, right? So if I'm going to sort all the edges of this graph, so I will have something like your 0 to 1 as first edge because it is having this 9 as weight. Then the second one should be your 3 to 4. It is 31. So the second one is your 3 to 4 because you got this weight as 31. Then we got thereafter we got, sorry, it's not gonna be the second one. 1 to 3 is gonna be the second one. So 1 to 3 is going to be the second one, right? Because it's gonna have the weight as 19. Now thereafter, once you know this 0 to 1, 1 to 3, then you got this 3 to 4. Then we have this 1 to 4. This is 42, right? So this is your number 3. Thereafter we got 2 to 3, then 0 to 2, and then 1 to 2 or 2 to 1, right? So the first thing first is that you need to have all your edges in a sorted arrangement. So once you have all the edges in the sorted arrangement, thereafter you need to add the edges with the shortest, with the smallest of the weights, right? So I'll add the first edge 0 to 1 with the weight as 9 in the tree. Then I will add 3, 1 to 3. So thereafter I'll add 1 to 4 with the weight 42, and thereafter I'm gonna add 3 to 4 with the weight as 31, right? So this is how I'm gonna keep on adding all the edges in the graph, but I need to ensure that there is no cycle. I gave this assignment as well. So we are not looking for the cycle. So there should be no cycles. You add and you check for cycles that there should not be any cycle. Guys, is the algorithm clear to everyone? Can I get an acknowledgement from all of you? So algorithmically, I hope this is not a challenge for you. So you keep on adding the edges in the tree. That tree will be known as minimum spanning tree. But at the same time, right, when you are adding your edges, so you need not to come up and form the cycles in your minimum spanning tree. So let's see how the cycle is going to be created for us, right? So now I'm going to run this algorithm. So just give me a moment here. So here you are, guys. You run this program now. So what you see is 0 to 1, the shortest edge has been added. Then the next edge was 1 to 3, it is added. Then we'll add 3 to 4. But the moment you are going to touch down your 1 to 4, so I think I did even a small mistake here. So this is so this is one small guys, just want to update. So after 1 to 3 we'll add 3 to 4, right? So this is not going to be the case here. So just a small rectification. So after 1 to 3 you gonna go to 3 to 4 because 31 is smaller than 42, and thereafter you are going to come back to this. Okay, so I just wrote in a different way, not just fond of using these pens and all here, so somehow, right? So coming up here now, when I'm going to come up and add this edge called 1 to 4 or 4 to 1, my question goes like this will definitely form a cycle, right? So how you will detect the cycle? So when I will say 1 to 4, it has to be left around, right? So 1 to 4, when you're trying to add, so you have to leave this part. So how you will come up and manage to detect a cycle in the graph? So Nanur says store nodes in set, and in case elements repeat, break. So Nanur, if you see 0 to 1, 1 to 3. So 1 is repeating twice, right? 0 to 1, 1 to 3. Then 3 to 4, right? So it is repeating twice. So set focuses on uniqueness. All right. So what I'm going to do is I'm going to give you some more time to think on it, right? In the meanwhile, we'll start writing the program where the first thing first is that you create a graph where you have these edges and then you sort these edges, right? So I'm going to add the edges and I'm going to sort them. So let us write a new Python file. This goes like your session number 36. So we already have created this graph program, if you can recall. So we are going to use the same graph program where we created the edge as class, and thereafter we got the class graph, right? So I'm just going to use the same program. So this was the previous discussion on Solin's algorithm when we did this part. So I'm working on this undirected graph, right? So we'll work on the undirected graph first. So we have the class called edge. We got a vertex 1, vertex 2, and a weight, right? And you are maintaining the attributes in the object edge, and get edge details, return back the edge along with the weight, right? So left is the vertex 1, right is the vertex 2, and middle is the edge. So you have this graph where we got vertices as dictionary, right? So I can write like this as well. So it's gonna be a dictionary, it's up to you. Then we got the function called add edge, where if the vertex 1 is not there in the vertices, you get the vertex 1 added in the vertices as dictionary. So this is the dictionary, right? Dictionary of vertices, to be precise. This is dictionary of vertices in graph. And you add these vertices in your dictionary as list. So this list is going to be your adjacency list for the current vertex. And once you add the data, what you were doing was you were appending the vertex to and the weight as a tuple in this adjacency list, right? So this was what we were trying to do. So who was adjacent to what? We added this part, and in case the graph is not directed, right? So the another use case was in case the graph is not redirected, directed. So we will be adding them both. This is what we were doing. All right, I think we have a query here. So now, Noor, just in order to kind of have the data for the vertex as well as for the weight of the edge, right? You need not to do that at the same time, right? This was just in our previous discussion. It was done to have the weight along with the vertex, right? So today, that is what today I'm not gonna work on the display part, right? So for the display part, what I'm gonna do is I'm just gonna have the vertex added, not the weight. So today for our algorithmic approach, right? That was for understanding of that you have the weight associated with an edge, right? When you are adding the vertex. So what we are going to do is we're going to maintain the adjacency list of vertices like this. So when I'm going to print my graph, right? So I will be only having the vertices in my graph, and there will be adjacency list which I can print. But at the same time, I don't have the edges in my graph, right? So when I'm going to print this adjacency list, I will be able to print the vertices. Of course, your vertex, when you are trying to add, right, it's a part of edge. So let me come here. For key in keys, you are iterating into the graph, right? And you're going to come up and print the key, and you're printing this vertices of key. So it means you are printing the list of your adjacency vertices. So I think this part of discussion has not been done by you guys, right? I think so. Okay, so coming here. So with this current code, let's try to run the program. So this is how it's gonna work for us. It's gonna give us these edges, and so initial number of vertices, and thereafter you add it. So print graph we added, we execute twice. So I can just execute once. So here we are, 5 vertices with the adjacent vertices which are being printed for us here, right? So the same program we have done multiple times now. But what I'm gonna do is I'm gonna give an input to the constructor called edges. By default, the value is going to be none. So let us maintain edges in the graph object. So I'll say self dot edges is a list, and at the same time, right, if these edges is not none, in case the edges are not none, so I'm gonna say for your edge in edges self dot add the edge, rather than putting it here. So rather than putting it here, I'm going to give the input of edges in the graph. Now it's very basic for us to understand, right? Assuming that you actually don't give the edges in the constructor for the graph, it is going to be none by default, and you are only adding the edges in case edges are not none. And in the add edge function, I'm going to come up and say your self dot edges dot append the edge. So this way, what we are doing is we are also adding the edges of the graph in this list called edges, right? So printing the graph is one thing. Now I'm gonna say define print edges. So here I'm gonna run this loop for edge in your self dot edges, print as edge dot get the edge details. So if you print the graph, thereafter you can now even say print me the edges. So here you are. So these were the edges which you added, right? This you printed off. Okay, so just give me a moment. So these are the edges right in your graph, but I just need to see where we are. Yeah, so here we are printing these edges, right? So I'll just move it from here. So I hope this is clear, right? So these are the vertices, number of vertices. This is the adjacency list, and this is your edge list. Can I get a smiley from all of you? Is the code one? Just kind of modified a bit of the previous program. Let me share it with all of you. So looking from this algorithmic approach, I'm gonna add these edges. So I have this 0 to 1 with 9, 1 to 3 as 19, then 3 to 4 as 31. So what I'm gonna do is I'm gonna add these edges into your graph. Rather than our edges, we'll add the same edges. So 0 to 1 we got 9, then 0 to 2 we got 75, then 1 to 2, sorry, 1 0 to 1 0 to 2 is done. Then we got 1 to 2 as 95. Then we have this 1 to 3 and 1 to 4 to be added. One to 3 and 1 to 4. So this was your 19 and this was your 42. Then 2 to 3 and 3 to 4 as in your next one. So these are the 6 edges, right? If you see, I'll run the program 0 to 1, 0 to 2, 1 to 2, 1 to 3, 1 to 4, 2 to 3, and 3 to 4. So these are the same edges, right? So you got 0, 1, 2, 3, and 4 vertices, 5 vertices, I mean to say, and 6 edges with the weights we have mentioned here, guys. So 3 to 4 is 31, right? 2 to 3 is 51. All right. So anyone with any query, can I get a smiley as an acknowledgement? I hope this is clear till now, how we constructed the graph. Now what I need to do next is I need to come up and have a new list of edges, right? So that list of edges must be sorted for us. I need to sort the list of edges. To run my Kruskals algorithm, I'll define this function which says sort edges. In order to sort edges, I need to create another edge list, right? So this is like edge list, which is going to be your self dot edges, and I'll put a column, right? So what I'm doing is I am creating a new list, edge list, where we are copying the data from self.edges. So we got two different edges, right? I mean to say two different edge lists, right? In case I will just do an assignment operation, then it's gonna be a reference copy. So if I will do it like this, it's gonna be a reference copy. So whatever I change in my uh, edge list, that will also modify your self.edges. So what I'm doing is I'm not going to come up and you know have a reference copy. Rather, I will copy the data. So more or less DP copy, which I'm trying to do here. Now we want to sort the data. Of course, we know the sorting algorithms. We can implement any algorithm and we can try sorting the objects, right? We have seen that. But let's explore some Python functionalities. So I'm gonna say from the operator import attribute getter. So this attribute getter can be used to sort the data for us. Let's see how. So I'm going to say edge list dot sort. So we're gonna sort this edge list, and we're gonna sort the edge list on a key, and that key is going to be attribute getter, and I'll mention the key as weight. So what exactly means by this, right? Attribute getter weight. So I want to sort the data because my edge list is a list of type edges. Edge is an object. So there is a key called weight on the basis of which I want to sort the data. So guys, can I get a smile here? Is this part clear to everyone? So I can even use this input called reversed. So this guy, if true, then the sorting will happen in a descending order. If you mention this as false, right, which is by default false, it will happen in the ascending order. Right? So when I say reverse as false, this means ascending order. So if you make it as true, it's gonna be descending order. So let us return this edge list. So if you want to sort the edges, so you should have these list of edges which should be sorted for us. So this was the first thing for your Kruskals algorithm. For Kruskals to run, we need to have sorted edges. Guys, what is the next step, right? The next step is that we run the algorithm called Kruskals. So Kruskals is an algorithm, but for my Kruskals to run, right, I need this edge list. So I'll just have this edge list as your self dot sort the edges, right? So you run this code sort edges and you get this list of edges. So I'm gonna say for edge in edge list, print me adding edge to minimum spanning tree, and let us even print this edge. So get the edge details. So I'll just come here and next I will say my graph dot Kruskals. So I'm just gonna say graph dot Kruskals. So these edges which we are printing, they were the part of your graph earlier, and when I will run this Kruskals, we'll see whether this edge list is sorted for us or not. So let's run the code here. So adding edge to MST, and here we are with the details of the edge. So 0 to 1 9, 1 to 3 19, 31, 42, 51, 75, 95. So this is your previous list versus new list. Can I get a smiley as an acknowledgement? I think the first step is already done for us. Sorting is clear to everyone, right? So we use the Python concepts rather than writing our own divide and conquer models. All right, guys. So we sorted this data, and now the next thing is for the Kruskal, I'm going to write this minimum spanning tree is an object of graph. So what we did, let's create a new graph object, right? So you got a new graph object which you have created, and you have to return back this graph object, return back this MST. So your minimum spanning tree is going to be a resultant of this function execution of Kruskals, right? So when you execute Kruskals as your algorithm, so you create a graph, a new graph, which we call a minimum spanning tree, right? So you want to find the distance in the graph. You want to find that kind of a path in your graph which will follow the shortest route by touching all of your nodes. So in the MST, we need to add edges, right? So adding edge to MST, you need to come up and say minimum spanning tree dot add the edge. Which edge? This edge you need to add, right? So in the MST, when you will add the edge, then this add edge function will work in the same way it was working earlier. So moving ahead now. So once you will get this MST, minimum spanning tree. So let's say running Kruskals to get minimum spanning tree. And here I'm gonna say print MST details. So for MST details, I'm just gonna say MST dot print the graph, and thereafter I can say MST dot print me the edges, right? So let's print the graph and print the edges when we run this algorithm. But this algorithm is quite incomplete, right? You are as of now just adding all the edges blindly, right? So the way you got the edge, you added the edge. The only thing is this, that you added all the edges in the sorted arrangement. So you haven't put any check as of now in the Kruskals algorithm. So what I need to do here, right? I need to check for the cycles in the edges when we are adding them in the graph, right? So I need to come here and cross check this cycle for us. So how are you gonna do a cross check? So when you add 0 to 1, it's perfectly fine. When you add 1 to 3, it's perfectly fine. 3 to 4 is fine. But when you add 1 to 4 or 4 to 1, this is a problem. So how are you going to manage this problem, guys? So let me open this statement here. Just give me a moment. All right, so here we are, guys. So now my concern is what? So I got this 0 as my first edge, 0 to 1. So at that time, we understand that 0 has only one neighbor, one adjacent node or vertex called 1, right? And 1 got this guy called 0. So when you added the first edge, 0 to 1, so 0 has 1 as neighbor, 1 has 0 as neighbor or adjacent vertex, correct? When you added 1 to 3, so when you added 1 to 3, so 1 got 3 as neighbor and 3 got 1 as neighbor. Now when you added 3 to 4, so 3 got 4 as neighbor and 4 got 3 as neighbor. Guys, can I get a smiley? Are we clear here? When I'm talking about this So when you're talking about this adjacent vertices, this is very much clear to everyone. Can I get a smile from all of you? So the moment I'm going to step into this guy called 4 to 1, when I'm going to add this 1 to 4 or 4 to 1 edge now, so what will happen? For this guy 1, I will have 4, and 4 for your 3. So coming up for your 3, you're gonna have this another element called 1, right? So what we will see is that the intersection, which is like the common elements of this guy 3 and 1, 3 and 4, I mean to say. So the common elements for these two sets 3 and 1, you have 1 as common. So you have this 1 as common, right? And when you come out with this 1 as common, right, and you understand that, okay, so for 3, 1 was already the neighbor, right? And for 4, you're also making 1 as neighbor. So there is some challenge here and there, right? Can I get an acknowledgement here? So typically, you need to check your all the adjacent vertices, and of course, you need to have the intersections on their sets so that we can kind of come to know whether they form a cycle or not. But I'm gonna write a very partial algorithm for you guys so that you can just scratch your head a bit more. So what I'm gonna do is I'm gonna write one small check here that how I'm gonna manage the cycle cross checking. So you add the edge, right? So the way you added the edge, so this was a code to add the edge, right? So the moment you added the edge, so you got this edge in your graph. So what I will do is I will say set 1 is going to be a set of minimum spanning tree dot vertices of your edge dot vertex 1. So same way set 2 is going to be for the vertex 2. So what I did, right, I actually created two sets of the adjacent vertices. So create set of adjacent vertices. Now I'm going to find their intersection. So intersection is to get the common elements, right? So there is a set 3, which is going to be your set 1 dot intersection with set 2. So let us print down the set 3 as well. So I'll print all these sets now, right? So print me set 1 comma set 2. All right, that's it. So when you run this program now, so guys, please have a look here. The very first edge which you added was 0 to 1 with the weight as 9. So 0 has neighbor as 1, adjacent as 1, 1 has adjacent as 0. So when you took the intersection for set 1 and set 2, there was nothing as in common. So the set was empty. So the length of set was 0, right? So when you added this 1 and 3, so for 1, the adjacent elements became 0 and 3, and for 3 it was 1. Again, the intersection will give you no result. You added 3 to 4, so for 3 you got 1 and 4, and 4 you got 3, you again get an empty set. But the moment you add 1 to 4, guys, please have a look here now. For 1, the adjacent vertices were 0, 3 and 4, and for 4 it was 1 and 3. So there is 3 which is common in these two fellows. So what we have done is we have got this common element. So now the length is not 0. Can I get a smiley? We were able to detect a cycle. An acknowledgement awaited from all of you. So Gurlibleen, Lavesh, Malika, Navnoor, Prab, Shivam and Tejeshwar, guys, I hope everyone is clear here. So the logic says, so Gurlibleen, can you please let me know where to repeat and what to repeat? So for the cyclic part, right? 1 to 3, 3 to 4 and 4 to 1. So how you will detect this cycle? How you will see that, okay, 1 to 3, 3 to 4 and 4 to 1 makes a cycle, that there is a triangle. So let's see how you're going to understand that it's a triangle, right? So for this two triangle, 1 has the neighbor 3, 3 has the neighbor 4, 4 has the neighbor 1. It makes a sense for us, right? So 4 has neighbor 1 and 3, 1 has neighbor 3 and 4, 3 has neighbor 1 and 4. So what I'm doing is I'm taking intersection on their adjacent vertices, right? So when you take the intersection on their adjacent vertices, in case the common elements come out for us, then that's gonna be a challenge for us, right? So it means that they have someone who is common in their neighborhood, so that may form a cycle for us. So good to go, Gurlevlin? Right. So in the next part of our discussion, now since you have already added the edge, so we are going to come up and say if the length of your set 3 is not equal to 0, right? In case it is not equal to 0, I need to remove this edge. So I need to write a function where I will say remove the edge. All right, so I want to remove this edge. So let's come here. The way you wrote this function called add of edge in your graph, same way I'm gonna write this function called remove this edge from the graph. So how you will remove the edge? So you will use the word remove instead of append. You don't create the lists here, so they are already created for you. So you just say remove it from the adjacent lists as well, right? So we got this remove function rather than the append function. So I'll remove the edge. So guys, let us now try to add till this part, right? So okay, so let's run this code and see what's going to happen. So what we see now is I'll just run the program and even write this part here. So removing edge from MST, right? So whatever the edge you are trying to remove, I'll just print out the details. So this everything is happening in this for loop for us. So here we are. So the moment you got this intersection for 0, 3 and 4, 1 and 3 as 3, so we are removing the edge. So 1 to 4 removed, if you can see, guys, right? So we sort of removed 1 to 4 over here. Now the next edge which you are going to add is this edge called 2 to 3. So I can just have a small print statement once this loop finishes. So here we are. So you added the edge, no intersection result, then again no intersection result, no intersection result. But the moment you got the intersection result, you remove this edge from the list. Can I get a smiley, guys? I hope this is clear to everyone now. So we got this intersection and we removed this edge 1 to 4. But at the same time, right, so you are adding this 2 to 3. So let's see, will 2 to 3 be added? So when you run this program here, so 2 to 3 is supposed to be added, right? The answer is yes. So our algorithm will add 2 to 3. There is no intersection result. Then for my next part, we need to see this fellow called 0 to 2. Now this should not be added, right? This shouldn't be added. But when I executed my 0 to 2 code, I understood that 0 has adjacents as 1 and 2, and 2 has adjacents as 0 and 3. So what we are doing, right? We are checking a cycle which forms a triangle. For that, our logic is working fine. But how about this rhombus, right? So the moment you got this 0 to 2, right? Now I need not to check with 0 to 2. I need to check with 0, 1, 2, 3. I need to check one more vertex, right? So this is what I'm leaving on you guys. So for our algorithm, it's gonna work for finding the cyclic part as a triangle, right? So this should be left around. We should not touch it. At the same time, when 1 to 2 you will try to add, it should also not be added, right? So you will find in our algorithm, when you were trying to add this 1 to 2, we got the common elements and we removed it from the edge. So the only problem which we got was that we got this 0 to 2 added in our graph, in our MST, which it should not be, right? So refine this algorithm. You only need to understand. So check for any cycle made by edge. Check for any cycle made by adding edge to graph. So guys, consider all the use cases here, right? So consider and think of all the use cases. So can I get a smiley acknowledgement from all of you? Are we good to go? So if you will see that this is our minimum spanning tree which has been created, right? So we were able to check with 1 to 2 and 1 to 4, but 0 to 2 was not on our list, right? So that was a challenge for us. So I'm gonna push this program over the GitHub. So this will be all for the day, and tomorrow we're gonna bring down something known as Prim's algorithm, guys. All right. So just give me a moment. So guys, anyone with any query here now? So I pushed this program over the GitHub, right? And at the same time, I'm gonna give you this. So you understood this algorithmic approach, I hope, at the same time, right? Okay, so tomorrow we're gonna see how we can run Prim's algorithm and how we can implement it, right? But consider this as your assignment at the same time. I have given you one, you can say, a kickstart how you can implement the algorithm, right? Don't forget that algorithmically you have to grow strong, right? It shouldn't be that you shouldn't be coding at the same time. So even if it's an online session, I will like to give you these kind of assignments where you should be trying your level best. So we'll most probably have a class on Saturday, right? And this is all. So once again, thank you so very much for joining in. See you tomorrow at the same time. Thank you, guys.